And we're going to look at an internal flow model. So we have an electronics enclosure, and a large percentage of flow consumers are doing thermal management for electronics. And we're going to play with a couple different heat sink configurations, or two different heat sink configurations, external versus internal fans, and the locations of the fans. And we'll use the general cloning process to do the first three, and then I built up a simple optimization or comparison study using the parameter study option inside of Flow. And we can see in this little video here that choosing the types of fans and the locations are really driving the behavior over by the heat sink. And in particular, that's where our microchip is at, and that's what we're really going to be concerned with at controlling the temperatures in the model. So generally, with thermal management, you know, airflow optimization is something that we're going to look out for, and we can't play with that using an FEA-based thermal solution. You know, all of our components, they're both sensitive and generating heat, so it's kind of a double-edged sword. We want to be able to choose a heat sink configuration that's most effective. In our model, we've got a fin design versus a pin design. And then we also want to make sure that our fans have enough capacity, given the pressure resistance we have, and given the proper amount of flow through the solution. And we will be using a couple items in the electronics cooling module. And these are dedicated tools specifically for electronics thermal management. And these include 2-resistor compact model. So we'll see this in our study. And this is where we're able to more accurately represent microchips and electrical components so that we can get better junction and case temperatures. And with heat pipe models, so you know, laptops, anything where we're looking to design low-profile electronics. Very often we're using heat pipes to move the heat from our chips to the heat sinks. There's a PCB generator that we're going to use in our model, and this emulates the thermal conductivity and specific heats of the PC board more accurately because, you know, they're laminar of copper and FR4 generally. There's also the dual heating capabilities. So a fuse, I call it the toaster effect. If we pass current through a metallic object, we're going to generate heat in the model. And then lastly, the electronics cooling module updates our library. So we have more fans, more materials, everything related to electronics. So there are, as I said, some of the biggest consumers of flow simulation are doing it for thermal management. Here's just a few customers of SolidWorks Flow that are doing electronics, and most of these folks are specifically LEDs since they are very sensitive to temperature. So let's get over and take a look at our model. We'll close our hopper. So now that we're familiar with the flow environment a little bit, we'll notice that there's 3 CAD configurations we're looking at, and there's 2 more generated by my optimization study. And this is our pin design heat sink with an external fan. And then we have a more standard fin design heat sink where we're using an internal fan. And what is inside this model? I like to think in terms of where's the heat coming in and where's the heat coming out. So if we scroll down our feature manager, it's a little more interesting than what we saw over there with the external flow problem. We have a few components that are just being defined as volumetric heat sources. And these are the less critical parts that are basically just adding heat to the system. And then the more critical component, the microchip, we have represented as a 2-resistance component. So if you look at a microchip spec sheet, you'll see a junction and a case thermal resistance, and that is the input to a 2-resistor compact model. And we have multiple configurations and packages represented in the electronic cooling database. And then we see that this is also inputting 15 watts. So how is the heat getting transferred through the model? How are the materials defined? Well, as we see up top, we can apply our material definitions to the different bodies in the model. And we can use the SOLIDWORKS Flow Engineering Database, or we can pull them over from the material database for structural analysis. The PC boards are a little more interesting, and we're using the PCB modeling function. And when we look at the definition of the PCB, just by clicking Create and Edit, we see that we define the thicknesses of copper versus the FR4, and then we have our base material properties, and SOLIDWORKS calculates an average or approximate thermal properties, taking into account the thickness and the individual material properties. So this gives us a better thermal definition of the PCB, rather than just assuming that the material is all FR4 or all copper. So we have our materials, they're transferring the heat inside. We have our microchip components and our volume goals that are creating the heat in the model. Now, how is this heat moving around? We have 3 fans defined, and these are idealized fans, and they're defined via a pressure curve. And then as you see to our left, we have multiple predefined fans, and this is one of the benefits of being in the cooling module. We're going to have a greater selection. Otherwise, if you have a fan with a customer spec sheet, we can go in and input the pressure flow relationships and then save them in the database for reuse. And then how is the air getting in and out? So I mentioned this is an internal flow simulation, meaning that our volume is basically capped off. And so we're defining our relationship with the rest of the environment via a few idealized boundary conditions representing internal environmental pressure. And then as the air is coming through these boundary conditions, we're representing a pressure restriction of perforated plates, once again using an idealized model from our engineering database for flow. And so we have perforated plates, and we can enter the information a few ways, the shape of the hole, the free area ratios, and then SOLIDWORKS will figure out what that pressure restriction is going to be automatically. So it saves us solution time. Obviously, when we're doing any type of simulation, small features such as perforated plates, we wouldn't want to waste computation time when we can just represent that essentially as a pressure drop. So that's the overall model setup. So there's a little more going on in here than in our external flow model, and we can just do a quick overview and display all of our callouts. And let's load up our results. So we'll start out taking a look at a cut plot like we did over in the hopper. And this is going to allow us to see, anywhere in the model what's going on. In typical SOLIDWORKS, we can take any plane and drag it and drop it and move it around. And we're showing our streamlines in this case. If we want to extract values at specific locations directly from our surface contour plots, we can just turn on the probe function and select specific locations. Also, we can add more parameters to look at that specific point. So if I wanted to know pressure, I can add that to my probe callout. Surface plots are another common way of looking at our result sets. And I want to see what are the temperatures on the heat sink, how do they look. So I can just say display the temperatures on the heat sink, and we can see how well is the air moving through and picking up the heat from the model. So the front end of the sink, where the air velocity is the highest, we're getting the most heat, and the fins are the coolest. But we're really not really using this heat sink to its full potential. It's pretty hot by the time we get to the end of it. So the fins are pretty tight together. We need to really push the air through this heat sink to make it effective. Another handy way of looking at flow simulation plots we haven't seen yet are what we call ISO surfaces. So the ISO surface just displays our parameter at a specific value. So right now we're displaying a temperature profile of 32 degrees Celsius. As I start to drag this out to the higher temperatures, we can see the ISO plot is adjusting. And now let's bring it down to 22 degrees Celsius, and we see we're encompassing more of the model. We can also have multiple layers of ISO plots. So let's include 22 degrees Celsius and 55, so where it's really hot. And then lastly, let's display the flow trajectories. So this is all fine and dandy, but what are the end results? We used our clone process to take our base model and copy it to 2 other design configurations. I want to know how they stack up. And my main concern in this case is really the temperature of the microchip. So similarly to the force goals that we created for the hopper, we have goals here that we're tracking the temperatures of the chips and our main chip. So we're getting max, min, and average temperatures of our chip. In 2013, we've added enhanced comparison capabilities. So of the 3 models in here, I want to compare what's the temperature of the microchip for the internal fan model against the external fan model, where we have them directly on the face, and versus the external fan model with the pins. Very simply, we can just click the compare button, and we can choose to compare goals, surface parameters, active scenes in the model. And so let's pull up a cut plot, actually, before we do this, so that we can look at both numerical data, and we can see why the numbers are the way they are. Okay, so here's a cut plot top view. Now we'll say compare. So let's include the active scene and our CPU temp as one of our comparisons, and then we can choose which runs we want to compare from. And this saves manually jumping back and forth and cutting and pasting our results or sending them out to Excel and doing our comparisons there. So this is going to load up the data for each configuration. It'll just take a second. And then we'll have a nice summary and then visual comparisons of the color cut plot. There we go. So the first thing that we'll look at is it compares the active scenes. So the internal fan model versus the external fan model, and then the external fan model with the pin heat sink. And then we have a table here of the heat sink temperatures. So the internal fan was okay. The external fans were working a lot better. And then the pin heat sink was just really not cutting the mustard. And when we looked at those flow trajectories, it kind of becomes obvious when we look at the flow pattern over the heat sink, and that the air is getting more directly forced through the thin fans in the heat sink with the external flow model. And it was really, when I looked at the model, it was because of the orientation or the location of the fan relative to that heat sink. So I wanted to do one more comparison study. In Flow, for 2013, we've actually enhanced the parametric studies that existed before. So now we can do multiple parameters in the model, and I'll start up a parameter study. So when we look at this interface, we can add simulation parameters. So if I click this button, we'll see that inputs to the flow model and the flow settings can become variables. And then Flow will automatically change those variables and rerun the simulations, such as our heat source. If we want to play with the power in our 2-resistor compact model, this could become one of our simulation variables. Or we can choose, additionally, dimensional parameters. So any of my mates or feature dimensions can be a variable. So let's take a look at something we might want to work with. So I'll switch over to the internal fan model, and I'm going to play with the internal fan location relative to the wall of the housing. So there's a dimension here that is controlling the location of the fan relative to the front end of the PC board. And that's when I'm going to want to make my parameter and run a couple different versions of the internal fan model by offsetting the fans closer to the heatsink. And we'll see here I've already created a design study where we're using that offset as a variable. And I've said I can use discrete values or a range of values. So I'm going to run that at a 1/4 inch offset and then a 3/4 inch offset. And I want to track the main chip temperature and my flow rates. And then this is going to give me 2 design points. And those configurations will automatically be created and run. So we see we have a couple different configurations that were generated along with the resulting flow models automatically. And I'll load up that result set. And so for an internal fan model, by adjusting the location of those fans relative to the heat sinks, I was actually able to get pretty decent performance, but still not quite as good as using the external fan model. So we had a main chip temperature of 50 versus 48. So that was a 1/4 inch offset from the end of the PC board versus a 3 1/4 inch offset. So flow simulation is a pretty easy to use tool. The interface is intuitive. We have our feature manager based model control. And you don't ever have to spend a lot of time importing and exporting neutral files. And then when you want to make design changes, you can use the power of SOLIDWORKS to reconfigure your model and then copy your simulations and rerun them. And then additionally, you can expand on those multi-run capabilities by using optimization tools to run multiple simulations, learning more about your product early on.